Thank you for a nice introduction. So we can start now. I will start presenting Fuertes, the Swedish Research Institute of Mining, Metallurgy and Materials. We are around 200 researchers located in Sweden, Luleå, which is in the north of Sweden, and Stockholm, capital. We have more than 20 years of hydrogen embrittlement research, and some of the new equipment that we are building up is autoclave here in Luleå, around 1,000 bar, plus minus 80 degrees. For my side, I'm a first year PhD student at Strenght with Luleå University Technology. Work as a researcher at the corrosion and hydrogen embrittlement group. And my PhD is part of a Finnish project, which it's a really it's an initiative between SSAB, LTU, and Sefer to promote steel industry decarbonization in the northern part of Sweden. And preliminary thesis title is Effect of Hydrogen Gas on the Properties of High-Strength Carbon Steels under use for storage and transport. So I will have a little introduction, then we go to the materials, methodology, results, and later summary of everything. As has been said here in this conference, hydrogen is really good for society. We want to achieve a decarbonization. We can use hydrogen as a fuel, and we want to build this hydrogen economy. But we have bad side is that hydrogen is quite detrimental for materials. We have this kind of, as you can see in this kind of images. Yeah. So I focus in high-strength carbon steels, which are commonly used in pipelines and storage vessels. I used to measure the mechanical properties under hydrogen. We use the slow strain rate test and fatigue test. And as long-term aims for my PhD, it's to measure the hydrogen embrittlement sensitivity of these steels, understand hydrogen high-strength carbon steels interaction in terms of solubility and diffusivity and trapping sites, influence of welding in this kind of steels, and the effect in service conditions. Today I will present two different materials with perlitic microstructure with yield strength of 385 and UTS of 535. Mainly elements are manganese and silicon. It has some aluminum, titanium, chromium, and main application is pressure vessels for moderate offload and low temperatures. It is a microstructure. And a magnetic steel with higher yield strength and UTS, and mainly the same composition, more or less. And it's used for fusion weld pressure vessels. And we have some granular magnetic matrix with some degenerated magnetic quasi-polygonal ferrite and polygonal ferrite structures. The method used is this whole specimen method. We use 200 bars pressure at room temperature. We optimized the inner surface to 0.1 micrometers and Ferrous rate of 0.41. We used a strain rate test, strain rate of power -6, and fatigue test, strain control mode, following this standard, and 3 different strain rates at frequency of 0.5. For hydrogen analysis, we use this TDS with mass spectroscopy and infrared quartz tube furnace. And well, everyone here knows how it's used. And the heating rate used for this project, we we are using the 1 degree per second up to 800 degrees, then hold that temperature for 900 seconds. So going to the results, we can see that there is more or less same behavior. We have degradation of elongation on both materials with a slightly bigger deviation for the magnetic carbon steel. But still, if we go, well, sorry. As I told you before, it was really low, 10 power minus 6 strain rate. So it was test of 98 hours in hydrogen and 141 hours in argon. And here we can compare both materials. We have some reduction in elongation and reduction in area. And we can see that the magnetic steel behaves a little bit better in this test. From this SST test, we performed the TDMS after removing the shoulders of the specimens, and we can say that this different hydrogen distribution in both materials with different trapping sites and different amount of hydrogen in both. Here we can see 3 different curves, one hydrogen test, one argon, and one reference. And the most important thing here within the argon reference is that we could see some kind of redistribution of hydrogen after this strain rate test, and in both kind of curves. This is in a numerical way. And of course, the ferritic perlitic has a higher uptake of hydrogen. If we go to fractography, it's really easy to differentiate which is with argon and which is hydrogen. The leakage zone, we will say is this one here. And this is post-mortem defects or fracture, because we test the specimens until leakage and then we pull apart the specimen to see fractography. So more closer looks, we have here the magnetic ferritic bands, and here more brittle quasi-cleavage structure. So we can say that the UTS is not affected in these materials, but we have elongation and reduction of area under hydrogen environment. Fractography says that we have some presence of brittle failure in hydrogen environment, and TDMS suggests that there is different distribution of hydrogen inside of the material in different trapping sites. So if we go to low cycle fatigue, we perform some different tests at 1.2, 0.6, and 0.3 strain rate amplitude. And we can see that there is a quite detrimental effect in hydrogen environment, being a reduction of 88% and 85% at this strain level, 74 and 60% in 0.6. And we saw that at 0.3% of strain range amplitude for ferritic steel, we see a really high number of cycles, which can be considered as that's not anymore low cycle fatigue. And here we didn't show any leakage in the magnetic steel. And this is a fractography. So if we compare this in hydrogen, this in argon, and it's possible to see some kind of bands of crack propagation. And this is a more magnification. You can see a ductile failure and some quasi brittle features. So as a conclusion, we could say that in these tested parameters, UTS properties are not affected, but we saw elongation and reduction of area in hydrogen environment. For fatigue test, as higher strain amplitude, we see a more dramatical effect in the reduction of fatigue life. And it seems to be that Binetic still behaves a little bit better, but still there is detrimental effect. Then we could say that hollow specimen method is, at least for a moment, suitable to evaluate the effect of hydrogen gas in this kind of material. And for future work, we will have the different carbon steels to analyze. We will study the diffusivity and solubility of these steels and understand the hydrogen-weld interaction. And thank you.